Assalamu alaikum and hello everyone. This presentation covers our Discrete Structures project, where CPI data from the Pakistan Bureau of Statistics was analyzed to study how price movements across Pakistani cities evolve over time. The project applies discrete mathematics concepts such as relations, graph theory, similarity networks, centrality metrics, and partial ordering to real world economic data. Throughout this presentation, an overview of the dataset, methodology, similarity computation, centrality analysis, weighting strategies, and final insights will be shared. This project looks at multi-year and multi-category CPI data between April 23rd and April 2025 by treating each CPI category such as food staples, meat, oils, utilities, and so on as a separate network layer. The structure of price relationships across cities can be observed. The project identifies how price similarity patterns change over time and which cities consistently remain central or become structurally dominant. This project analyzes how the price movements across cities behave month by month. Using CPI data from the Pakistan Bureau of Statistics, similarity is computed between cities using cosine similarity, which measures how similar their price patterns are. These similarities form a network where each city is a node, and similarities above a threshold create edges. Graph theory is used to identify central cities. Temporal ordering is applied to see how networks evolve over year to year, and weighting strategies are used to compute influence scores. Ultimately, this helps determine which cities act as economic influencers in Pakistan's price system.
So to start with the data preparation phase, we pulled monthly CPI files from the Pakistan Bureau of Statistics for April 2023 up to onward. The dataset had 17 cities and hundreds of commodities, but to make the analysis more meaningful and avoid noise, we applied two major filters. First, we selected only the 8 major cities with the most complete and consistent CPI records. Second, we reduced the raw commodity list down to 51 key items and grouped them into 7 main categories like food, meat, oil, fruits, essentials, etc. After loading the files, we merged, cleaned, and structured everything month-wise and city-wise. This gave us a clean foundation to start building our mathematical model. Now moving on to how we actually model the data mathematically. For each city, we created a CPI vector for each category. This vector represents how the prices in that category change across the months for that city. For example, for Lahore in the food category, the vector would contain the monthly prices of all food-related commodities over 2023, 2024, and 2025. So essentially, each city becomes a point in a high dimensional space. Each category becomes one vector, and each vector captures the price trend over time. This structure allows us to compare cities mathematically, not just visually. To make sure all cities are comparable, we applied z-score normalization on every price value. The formula can also be seen in the slide. Normalization is important because some cities naturally have higher price levels than others. Without normalization, those cities would artificially appear more different even if the pattern of their price change is the same. After this step, our data had mean almost equal to 0 and standard deviation almost exactly 1, so normalization was successful. Once all CPI factors were prepared and normalized, we computed cosine similarity between every pair of cities. The formula can be seen in the slide. Cosine similarity measures how similar the shape of two price trends is. Even if the prices are higher in one city, the similarity is high if the moment is the same. A higher threshold means that only very similar cities will connect, so the network becomes sparse. A lower threshold makes the network denser. For our project, we selected a threshold of 0.85. This is a strict threshold, and using this value, we generated binary adjacency matrices, weighted adjacency matrices, and full similarity matrices for all city pairs. In cell number 1 of the code, we start by connecting our Google Drive so that all our files can load properly. Then in cells 2 and 3, we install the libraries needed for data processing and analysis. In cell 4, we set the folder path to our drive, and in cell 5, we define the 7 product categories that we will use in the project. Next, in cell 6, we load all the Excel files. This step reads the exact format of the data and prepares everything for filtering. Then in cells 7 and 8, we filter the data into two years, select the top 8 cities, and organize the information across 51 commodities. In cell 9, I along with my teammate normalize prices using the z-score formula. Then in cell 10, we create the cosine similarity function to compare city price patterns. Cell 11 builds the adjacency matrices, and cell 12 generates all similarity matrices and adjacency results. In cell 13, we test different thresholds to see how the network structure changes, and cell 14 displays sample outputs. Finally, cell 15 gives a complete summary of this whole thing.
This slide explains how we compare network structure across years. We check if the edges of year y are a subset of those in year y prime. If so, year y is less connected. The code also verifies partial order properties, reflexivity, since every graph is a subset of itself, antisymmetry, ensuring two years are identical if their edges match the set, and transitivity, so subset change consistently across years. This forms a clear temporal hierarchy. Moving on to the next slide, here we visualize the temporal hierarchy using Hasse diagram. Each year is a node and we compute all pairwise subset relations. Redundant edges are removed to keep only minimal covering relations, giving a clean diagram. We repeat this per category, showing which years are strictly more connected and capturing the structural evolution in a minimal interpretable way. This slide focuses on node level importance. Degree centrality counts direct connections, closeness measures access to all nodes, betweenness captures nodes that act as bridges, and eigenvector centrality reflects influence from well-connected neighbors. Together, these measures reveal which node dominate locally, provide global access, broker interactions, and gain influence from their network positions. We start by computing pairwise similarities of city price vectors to create agency matrices reflecting economic behavior. Using multiple similarity thresholds and weighted and both unweighted schemes, we construct network and store them as pandas matrices, network KX graphs, and dictionaries organized by year and category. For each threshold and weighting, we compute centrality matrices, degrees, closeness, betweenness, and eigenvector via a centrality analyzer to identify structurally influential cities over the time. Visualization tools network.visualize, plot centrality comparison, and visualize compressed Hasse provide interpretable layouts side by side, and temporal Hasse diagrams offering a comprehensive view of how price similarity network evolve and reorganize.
This section brings together the four centrality measures computed earlier: degree, closeness, betweenness, and eigenvector. After applying min max normalization, these measures are combined to compute influence scores at both the category level and overall yearly level. To understand how different assumptions change the rankings, four weighting schemes were implemented: equal weighting, correlation based, entropy based, and category importance weighting. Here are four weighting strategies. Equal weighting gives the same importance to all metrics. Correlation based weighting reduces weight for redundant or highly correlated metrics. Entropy based weighting increases the weight of metrics with high variability across cities. And category importance weighting adjusts influence scores according to the economic relevance of CPI categories such as food or utilities. For each weighting scheme, influence scores were computed using metric weights and then aggregated using category weights. After this, the top 5 most influential cities were extracted. Bar charts were generated for each scheme along with the combined comparison plot and ranking tables. This helps visualize how city rankings shift when the weighting method changes. Here I'm walking through how I compute and visualize the weighting schemes for our city influence analysis. I start by loading all the centrality CSVs from Drive. Each file represents a specific year and category and contains degree, closeness, betweenness, and eigenvector centrality for every city. I clean the files, ensure the city column is correct, extract the year and category from the file name, and then normalize all four centralities to the 0, 1 range so that they're comparable. After processing, I compute three different influence scores. S equal gives all centralities the same weight, which serves as a simple baseline. S score uses correlation based weights, meaning metrics that overlap too much with others get downweighted and unique metrics get more importance. S entropy is variation based. The more a centrality differentiates cities, the higher its weight. Then I apply economic category weights, alpha, and aggregate across categories to get a single yearly influence score for each city. After this, I generate tables and visualizations to compare how the top cities change under equal correlation driven and entropy driven weighting. This helps us see both the stability of rankings and the impact of different weighting choices.